He is a staff scientist at Las Cumbres Observatory and will be talking to us about exoplanetary spin-orbit misalignments and implications for planetary migration and dynamical histories. Take it away.
Hi everyone. Let me just share my screen. Okay. And that look good?
Yep.
Okay, cool. So yeah, hi everyone. I'm Marshall. I started as a staff scientist at Las Cumbres Observatory about a year ago, and I'm glad to have this opportunity to introduce myself to all of you and tell you a little bit about some of my research. So I'm going to be talking today mostly about exoplanetary spin orbit alignments. So just to make sure that we're on the same page, this is a quantity that Juliet Becker talked about a little bit in her talk earlier. It's just the angle between the stellar spin axis and the normal to the planetary orbital plane. This is typically only able to be measured for transiting planets. And I'm showing that geometry here. The planet transits along this black line from left to right. The vertical arrow is the projection of the stellar spin axis, and then the spin orbit misalignment that we measure is this angle lambda here. So that is about 0 for well-aligned prograde orbits, 90 degrees for polar orbits, and about 180 degrees for retrograde anti-aligned orbits. So I'll talk a little bit more later about how these are actually how these are actually measured. But over the past 15 years or so, this quantity has now been measured for over 100 transiting exoplanets, mostly hot Jupiters. And it's been known for about 10 years since a paper led by Josh Wynn that these at least for hot Jupiters, these spin orbit misalignments correlate with the stellar effective temperature. For FG and K stars below the Kraft break at about 60 feet, 250 Kelvin, hot Jupiters are mostly well aligned. But for hotter stars, there's a much wider range of misalignments with a lot of polar and even retrograde orbits. This pattern is thought to be due in large part to tides. Planets around cooler stars are able to quickly damp out misaligned orbits, whereas those around hotter stars aren't. However, it's still unclear how these misaligned orbits are produced in the first place. There's been a lot of theoretical work on this over the past 10 years. I don't mean you to for you to read this entire slide. The point is mostly that there's been a huge number of mechanisms proposed for generating misaligned orbits, which generally fit into two categories. Either the misaligned orbits are caused by high eccentricity migration that brings the hot Jupiters close to their host stars where we see them today, or the misaligned orbits are caused by some other mechanism having to do with stellar physics, star formation, or other dynamics that's unrelated to the migration itself. And while there's been a lot of theoretical work on this, the observations still haven't been sufficient to distinguish among these models. So I'm going to be talking about a couple of different pathways forward for this. So horizontal analysis of the population of hot Jupiter spin orbit misalignment measurements. For a lot of this, I'm modeling them as a Fisher distribution, which is defined here. It's qualitatively similar to Gaussian distribution on a sphere. And this kappa parameter describes the dispersion of the distribution. I'm using the Bayesian methodology for population analysis that was introduced by Dan Fabrici and Josh Wynn in their 2009 paper. So I'm going to be showing several plots like this. These show the value of kappa that I've inferred from the distribution of measurements for a given population. Smaller values of kappa correspond to more isotropic distributions of these spin orbit angles, whereas larger values of kappa correspond to more aligned orbits. Here I'm showing the distributions for the FGK stars in blue, those cold stars, versus the hotter stars in red and magenta. And this quantitatively confirms the pattern that's been seen for the last decade, that the FGK star hot Jupiters are more aligned, preferentially more aligned than those around hotter stars. And then I can also do a mixture analysis of two Fisher distributions. So I'm showing here is I basically take running 10 running bins of 20 planets in effective temperature to basically see how the population changes over as effective temperature changes. And this is actually consistent with the entire population of hot Jupiters being drawn from a more or less isotropic population, a more or less aligned population, whose parameters don't change that much over the effective temperature range spanned by the observations. But what changes and causes the pattern that I showed earlier is the fraction in these two populations. For the cool stars, only about 20% of the planets are in the isotropic population, whereas more like 80 or 90% for the hotter stars. And interestingly, the transition between these two regimes isn't just a sharp transition at the Kraft break, but rather more gradual. There's still a significant population of misaligned planets even for early F stars, or excuse me, aligned planets even for early F stars. We can also look at correlations between spin orbit misalignments and other parameters. One particularly interesting parameter is the stellar metallicity. Rebecca Dawson and Ruth Murray Clay had a paper a number of years ago where they found that eccentric warm and hot Jupiters preferentially orbit high metallicity stars. They interpreted this as evidence of planet-planet scattering, since these high metallicity stars should preferentially form the systems of multiple closely packed giant planets that are the initial conditions for planet-planet scattering. And if these spin-orbit misalignments are also generated by planet-planet scattering, you might expect a correlation between the spin-orbit misalignments and the metallicity. However, this is not the case. When I split the sample for the and early F stars that have a lot of misaligned planets on the metallicity, the high and low metallicity stars have basically statistically indistinguishable distributions of misalignments, and this, at least within this this picture, this disfavors planet scattering as the cause of these misaligned orbits. There's a couple of caveats, however, this is not a uniform sample of metallicity measurement, so that could disguise any small trends. And these are also hot stars, where subject to settling of heavy elements within their radiative outer atmospheres, which could suppress any trends that were initially present. Another thing that I can look at to try to get misalignment mechanisms is young planets. Here I've color-coded the misalignment mechanisms by the timescales in which they operate, which vary a lot from less than 10 million years up to hundreds of million years, or even a gig year. So if we can observe planets that young planets where some of these mechanisms haven't yet had time to operate, we can potentially start to disentangle among them on that front. There's actually been a lot of work on this over the last year, thanks in large part to young planets discovered by K2 and TESS. Just highlight a couple of those that I've been involved in. Working with Andrew Mann and colleagues, we observed with HARPS North Roster McLaughlin measurements of HD 63433b, which is the inner planet of two transiting super-Earths around a 400 million-year-old star in the Ursa Major moving group. So as a planet transits a rotating star and blocks regions um, you, you get this velocity anomaly during transit, and the form of that tells you allows you to measure the spin orbit misalignment. And here, this planet is in a prograde orbit. And then here's another in prep young planet that I observed. We couldn't get a full transit, but this also indicates that this planet is also prograde, which is true for all of these other planets that have been published in the last year or so. Although one caveat here is that these are all much smaller planets than the hot Jupiters that I was talking about earlier. So just to wrap up quickly, look ahead, there's a lot of good prospects for observing more smaller and longer period planets. On the left here, I'm showing the measured spin orbit misalignments as a function of the orbital distance. There's a lot of hot Jupiters, but only a handful of these longer period planets. I think there's great prospects for measuring spin orbit misalignments for these longer planets like Umpaldalba talked about earlier. Thanks to Tess and Kepler, the planets they've found. And then also thanks to planets discovered by Tess and new and future facilities such as NUID and high resolution spectrographs on the 30-meter class telescopes. We should be able to measure the spin orbit misalignments for a sample of hundreds of small and long period planets over the next decade, which will give great insights into dynamical histories of exoplanetary systems. So I will conclude by leaving up my conclusions in graphical form and hopefully have time for a few questions. Thanks.
Yep, there is indeed time for some questions. Please feel free to put them in the Slack channel. I don't see any questions yet, so I will use Chair's privilege to ask a question. You mentioned that you didn't see any direct correlation between metallicity, for example, taking the caveats of not having a uniform sample. Did you try to see if there were any other correlations with any other system parameters?
Yes, yeah. Look at other system parameters as well. One that I show here that didn't have time to talk about, but has also been known for a while, is that more massive planets tend to be well aligned, whereas there's a greater dispersion for less massive planets. This is again attributed to tides, as tides act more quickly for more massive planets. Then I've also looked at other parameters like the orbital distance and the eccentricity of the orbits, and don't see any correlations there either.
Okay. Yeah, it's always interesting to try to find correlations in data.
Definitely.
I see there's someone typing, so we'll give that a minute. Okay, a question from David Ciardi. Hi, Marshall, nice talk, and I love the polar plots. Can you comment on the extending the Rosser-McLaughlin technique to lower mass, small radii planets, and exploring those architectures in comparisons to the larger planets?
Yes. So I think that's going to be a really great area which you can push forward over the next few years. TESS is really enabling that by finding these small planets around bright stars where it can really get enough signal to get these relatively short but high signal noise spectra like you need like we did for HD 63433b. So I think with test planets and current and new spectrographs like HARPS North, NUID, that there's great prospects for this over the next few years. And this will really of the insights into the dynamical histories of these planets. So especially you can do things like trying to get at the Kepler dichotomy. One of the proposals for that is that single transiting planets should be in dynamically hotter systems than multi-transiting planets. So you may be able to look at that. Look at ultra short period planets like Juliet was talking about in her talk earlier, and also doing things like we might even be able to measure the mutual inclinations between planets and multi-transiting systems by measuring the spin to orbit misalignments on both planets. So I think there's a lot of really exciting things we can do over the next few years for small transiting planets.
Great, awesome. I think that's all the time for questions. Thank you again, Marshall. Our final